Thank you everyone for coming. Today, Dr. Salim, Associate Professor of Mathematics in our department, and he was kind enough to lend his time and his expertise to help us with this topic. So he will be talking to us about principal component analysis. And just a small correction in the title, Math 692, it's not a graduate seminar. It's actually numerical optimization. So this exercise that we are doing is part of a course. It's part of the students' grading policy. So the students, they prepare presentations in different topics that helps their understanding in the course. And of course, we'll we ask experts to also broaden the background of our students. Again, I thank Dr. Salim, and I invite him to give his talk. Thank you, Dr. Salim.
Okay, thank you. Good morning, everyone. So thank you for joining. Today, I'm going to talk about principal component analysis, and mainly about positive definite matrices and singular vector or singular value decomposition, mainly called SVD. So this is the outline of the presentation. I'll just go through basic linear algebra concepts quickly. I'll talk about positive definite matrices, about singular vector decomposition. I'll move on to principal component analysis, and I'll talk about a couple of applications. So just a reminder about the inner product of two matrices in linear algebra. Usually what we do usually is to multiply, of course, if A and B, they share, of course, A has the same columns than the number of rows in B, then what we can do, we can say that the product here is defined, and we can simply compute it by arranging such that at the intersection of every row index of I and column index of A on column index of B, we can place just the sum of the products of the items row by column one by one. So this is basic, but we would like to have a different view on this product. We usually call the dot product in vector multiplication or dot product in matrix multiplication. So this is what we have been used to see, okay? But there is another way to see it, which we call the outer product. In fact, the same product, you could obtain it just by multiplying the reverse way. Let me explain it in detail. In fact, if you can move on and take the product of the sum of the products of the columns of A by the rows of B. Okay, I repeat, the columns of A by the row of B, they lend you exactly the same thing. Okay, most of us have not been used to seeing this, and this is exactly the main idea about, in fact, what we'll call singular value decomposition or principal component analysis. So we can see, for example, that if you multiply this column here to 1 by 3, 4, 6, well, it gives you a 3 by 3 matrix, simply just because, well, the first column has 3 rows, and the second vector has 3 columns. Well, even if they share 1, which is the number of columns in U and the number of rows in B, well, you can obtain a 3 by 3 matrix. Okay. Well, this UVT, well, is a one-dimensional matrix, of course, okay? And the main target is to write a matrix as a sum of ranked 1 matrices. Okay. So let me move on a little bit. So this is just a simple reminder, of course, if you can apply the transpose, you see that the transpose of, let me close this, please. It's bothering me a little bit. I'm still appearing in my screen. Okay, so you can see that now we've seen the product of two matrices as an inner or outer product? Well, so the main idea about what we talk today is to see a matrix AB as a sum of rank 1 matrices. Of course, in data science or principal component analysis in particular, we're not generally interested in dealing with matrices with 0 rank. So we'll write down a matrix AB at the sum of the products of, let's say, columns by rows, okay? So for instance, you can see that AB here, which is the product of 2 by 2 matrices, you can detail it as the product of 1, 3, the first column in A by the first row in B, plus the product of the second column in A by the second row in B, and you could obtain the same thing. In fact, you obtain a sum of 2 matrices, and at the same time, you exactly the same thing that you could have obtained by doing a regular inner product. So in fact, those pieces, the UVT we obtained here are the rank 1 matrices that decompose the AB matrix. So this gives an idea about a general topic in linear algebra we call factorizations. And if you have attended any linear algebra course, you have seen at least one of these factorizations. So mainly, maybe the most trivial one is what we call, first of all, the LU elimination or the LU factorization, where L is lower triangular and U is upper triangular. We have also what we call the QR factorization, where in fact Q has orthonormal columns. It means that QT times Q is equal to I, and well, the matrix R is upper triangular. Then we come to, let's say, one of the most important one, which is S equal to Q times lambda QT, which is what we call the spectral factorization, where S is supposed to be a symmetric matrix, and we have somehow something that works for any symmetric matrix. Then you can see that you can put the eigenvalues of S in lambda and the eigenvectors of S in Q, and you can obtain a beautiful factorization, which is very often used in principal component analysis and time series and econometrics, wherever you go. A more general way to see this is that when A is not here, this matrix is not symmetric. Well, what you can do, you can put the eigenvalues of A in lambda, and you can still have the eigenvectors of A in X and X minus 1, of course, when you do X. Okay? But if you generalize this, you come up with non-square matrices A, you can obtain this beautiful thing we call the singular value decomposition of any matrix A. So just to give you a brief idea, if you never heard about this, you already heard, I'm sure, about Taylor-Maclaurin series. So what does Taylor-Maclaurin series? It approximates a function at a given point by an n-degree polynomial, right? So we are using an f-degree polynomial to approximate the value of a function at some point. Well, this does somehow a similar thing. It approximates any matrix A by a kth rank matrix. So a matrix with a lower rank, and the main target is, let's say, to extract the most important part of the information contained previously. Okay. So, for example, in image compression, in principal component analysis, we focus on singular value decomposition. Okay. So basically, to give you the idea right now, just as a preview, in fact, the sigma here, the capital sigma, will contain what we call the singular values of A, and the U and VT, they will contain the left singular vectors and the right singular vectors. So we don't talk anymore about eigenvectors and eigenvalues. So let me move forward to what we call the part that is very close to numerical optimization or to optimization in general, which contains, we talk about positive definite matrices. So what is a positive definite matrix? It is a matrix that has all positive eigenvalues. Remember, eigenvalues are obtained when you solve the equation setting the determinant of A minus lambda I equals 0. Okay, so basically you're solving nth degree equation. So it is possible somehow that the lambdas end up to be complex numbers. Well, a positive definite matrix doesn't give you complex eigenvalues. More than this, it gives you positive eigenvalues. So it is possible to verify for a positive definite matrix that the positivity is checked out without even computing the lambdas. Okay, so I'll go through a couple of things how to check this. For example, what we call the energy test. If you multiply, put S between X and XT, you end up with a always positive polynomial. This is what you call the energy test. Other tests exist. For example, the leading determinant test. And the main goal, for example, when S is defined to be positive here, you end up with a kind of factorization that is QT times Q or AT times A. Okay, where the columns in A are independent. So, for example, one of the main idea behind the energy test, in fact, that when you do this product xt times xx, in fact, you get the square of the magnitude of the vector ax, which is supposed to be positive. So that's why we're talking about the energy test. And for example, this matrix S, well, you can write it as AT times A or A and MT as you wish, because basically it is positive. So the main test we use generally when we talk about positive definite test, and this is what we show to the students, and almost everywhere we go, this is the fastest test or the quickest test, which is the leading determinant test, which basically is based on the idea that if you take the submatrices obtained one by one, when you write every time one row and one column, they lend you a positive determinant. So for example, you can check out that for this matrix here, you have a positive subdeterminant here 2, then the next one is 2, is 3, the next one is 4, and all these leading determinants are positive, and that's in that case we have passed this test. This matrix is positive. Okay, and in fact, these leading determinants, they have some importance because they are related to the pivots we obtained in the LU elimination. Okay, in fact, if you can check that for this matrix, for example, S, I'm having here 2 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. If I perform the LU elimination, I have a lower triangular matrix, an upper triangle matrix. So this is L, this is U. And in fact, the leading determinants are here on the diagonal of U. And in fact, what you could obtain here, every time you have dk over dk minus 1 on the diagonal. Okay, so some guy got the idea to perform a factorization based on this, Cholesky. Cholesky proposed the Cholesky factorization, where based on the fact that the matrix is positive definite, well, he can pull out he pulls out the leading determinants here, their ratios. He inserts them in a kind of diagonal matrix where everything is 0, and just put the leading determinants there. And he obtained the kind of factorization, which basically gives him the A and AT we were talking about. Okay, so this is the principle of Cholesky factorization. How to obtain A and AT. I mean, how to write any positive definite matrix as a product of a matrix A and its transpose. Okay, of course, this is very particular to the case when we are having a positive definite matrix, and the idea is that, well, you take the square roots of the pivots you have there, or the ratios of the leading determinants, and you put them on the diagonal, and you can continue. So positive definite matrices, they have this very beautiful property that they do provide positive eigenvalues, and they are generally easy to verify. Okay, so one of the applications in minimization. So for example, in minimization, we generally are looking for what we call positive definite or positive semi-definite matrices. And we have a definition that says that if you have a function, for example, here there are 2 variables, If the gradient is 0, I mean the partial derivatives are 0, and if the what we call the Asian matrix obtained by the second derivatives is positive definite, then we do have a minimum at x0 by 0. Okay. The main idea is that the graph goes upwards whenever the second derivative matrix is positive. Okay, so you are in fact at the minimum. So for example, for this application, I do have f of x equals 3x squared plus 2xy plus 4y squared. And if you compute the first derivatives, okay, the f of dx and the f of dy, well, you could obtain just two simple, beautiful linear equations here, considering the setting of the function. And you have a solution which is 0, 0, but what you need then is to show that you do satisfy this minimum requirement, this minimum, the fact that you do satisfy what we call the second order condition, or the fact that the Asian matrix is positive definite. So you compute the second derivatives at 0, you place them in your Asian matrix, and you can see, well, this 0, 0 is in fact your minimum. It satisfies let's say the definition. Okay, so, but we can move on. This gives the idea to develop something else, which what we call the singular or single vector decomposition. So it is based on the fact that these beautiful positive definite matrices, or the real symmetric matrices, they are the best. Okay, they do have real eigenvalues, orthogonal eigenvectors. They come out of nowhere. They are orthonormal or easy to get to orthonormality. So it's beautiful. But for other matrices, well, the eigenvalues could be complex, and the eigenvectors could be non-orthogonal. So, for example, if A is not squared, and you are trying to find Ax equals lambda x, basically you are trying to solve the eigenvector problem. It is impossible because A is not squared, principally. And what we needed is an idea that succeeds for every matrix. So the singular value decomposition fact fills this gap in a perfect way. Why it is important? Because in our applications here, most of the time, we do not have square matrices. Okay, so A for us is often a matrix of data, and the rows could tell us, for example, the age, height of 1,000 children. So basically, one of the dimensions here, 1,000, and you have just two criteria, age and height. So the matrix is not square. So unless the height is exactly proportional to the age, which cannot happen, the rank is hard to. So that matrix has two positive, in fact, singular values, we call sigma 1 and sigma 2. And the key point is to compose the matrix in the sum of rank 1 matrices. So the key point is that we need two sets of singular vectors, U and V, to be able to write A at the sum of two rank 1 matrices. So let's give the general definition. The general definition is to be able to write a matrix with rank K, matrix A with rank K, as the sum of matrices we call AVs, or we call sigma. In fact, we call A and Xi, if you wish, when I runs from 1 to R. Okay, and every one of these matrices obtained by a sigma, a singular value, a singular left singular vector, and the right singular. Okay, these are the relations that need to be satisfied, and in fact, every U here needs to satisfy this equation. Okay, so for a real M by N matrix, the N right singular vectors V's are orthogonal in R, and similarly, the left singular vectors used are also orthogonal in Rn. So in their own subspaces. And we will have R positive singular values descending in order. And remember, R is the rank of A. And of course, the remaining is a null space. So for example, this is what is the, let's say, the sketch of what's going to happen. So A is equal to the U's multiplied by a sigma matrix, a large sigma matrix, and we place the sigmas here, the singular values in the diagonal. Basically, you have zeros here, and Beyond the rank R, well, you have just zeros. And I place it here, the right singular vectors in my column. Okay? So basically, this is the main idea about singular vector decomposition. Singular vector decompositions, decomposition would allow us to write a beautiful matrix of data into the sum of k rank 1 matrices. So this allows perfectly to compress the information or to extract the most important part and even to approximate the matrix of that. For example, I'm showing a small example here where we have AV. So our matrix here basically is the 1, 3, 0, 4, 5. I have the vectors that do form V. So basically I have two right singular vectors, 1, 1 and minus 1, 1. And dividing by their norm, I have an orthonormal vectors. And on the other side, I have the U's. So I have two different left singular vectors, 1, 3 and minus 3, 1. You can see that their dot product is 0. So they are perpendicular, they are orthogonal. And here we place it the singular values, 3 root of 5 and root of 5. Yeah. So if you can study this matrix A, 3, 0, 4, 5, you will have the singular values I do have here, the left and right singular values. Now the question is how to obtain this. Well, to obtain this, the idea is simple. To obtain this, the idea is simple, is to, sorry for that, the idea is to work on A times AT and AT times A. And A times AT, whatever is going to happen, even if A is not squared, so this is a particular case where A is squared just for simplification, but A times AT or AT times A are two different symmetric matrices. So they are positive definite, so it's easy to get real value and positive eigenvalues. And basically, the left singular vectors are obtained from one of these two symmetric matrices, and the right singular vectors too. And what is going to be left is that the singular values here are just the square roots of the eigenvalues of the common eigenvalues of these two symmetric vectors. So this is basically what I'm saying here. So the columns of V are orthogonal and the columns of U are orthogonal. And in fact, those columns are unit vectors, so they are not only orthogonal, but they are orthonormal. So I was just talking here about explaining how it was done. I will come back to it, but let me also show you something else. So the idea is not to decompose in any manner, but to decompose in a way that we get the right approximation, or the approximation that lends us the closest as possible to our own matrix of that, or our data matrix. So here, for example, here I'm saying this is the target, okay? So what needs to be understood, just a reminder, so it's like that, like other factorizations, like the LU elimination or the QR or the spectral factorization, the idea here is that we are going to separate the matrix into rank 1 pieces. So a special property of the SVD is that those pieces come in order of importance, which means that the first piece, and this is the most beautiful thing, the first piece we're gonna come up with, sigma 1 U1 B1T, is the closest rank 1 matrix to A, which means you can probably summarize 70–80% of the information contained in A in just one rank 1 matrix, which means the product of, as we detailed in the inner product, the product of just one column by one row, and just a scalar in front, a real number in front, which is positive. So more than that is true, the sum of the first K pieces is the best possible rank K. The same way we said with Taylor-Maclaurin series. So the best approximation as a polynomial to the value of your function at a given point is a polynomial, and you can use the n-consecutive derivatives. Okay, so here the Eckart-Young theorem says that what you could obtain when you write the AK here approximation, which is the sum of the first K singular value, single vector products, you get in fact the best approximation in rank K to your own matrix A. So if B has rank K, any other matrix B that has rank K, the distance from A cannot be less than the distance from A to A. So this is what Picard and Young said. Okay, so we are not only having a way to decompose a matrix, but we have the best decomposition of the matrix. How to do it? This is the mathematical stuff. So this is what I said. We use the two symmetric matrices AT and A, and AAT. We get the eigenvectors and the eigenvalues for both of them. They do share some common eigenvalues, and these shared eigenvalues are our singular values for them. I mean, using their square roots. So the SVD is obtained just, it is summarized in the definition. The SVD is obtained with V as orthogonal eigenvectors of ATA, U as orthonormal eigenvectors of AAT, and the sigma 1 squared to sigma r squared are non-zero eigenvalues of both AAT and AAT. Okay? Of both, I'm sorry for the miswriting, should have been ATA and AAT. Okay, so just a simple example. Here again, the same matrix. I'm decomposing how we got these things. So 3045, I computed ATA, which is symmetric, as you see. Similarly, AAT, symmetric. And we can obtain the common eigenvalues, sigma 1 squared and sigma 2 squared, 45 and 5. The eigenvectors of ATA are 1, 1, 1 minus 1. They are orthogonal. And we can obtain from them unit vectors, just dividing by the norms of the two first vectors. Similarly, we can do the second matrix. And for the second matrix, just to be able to fit this decomposition, we're going to write every one of the U's here as AVI divided by sigma I. Okay? So basically, from the VI's, we can obtain UI's, as we said in the first definition. And this is how the work is done. Okay. We've sent you the slides if you want to dive deeper in these in this computation. So at the end of the day, you get a matrix A, which writes as U times capital sigma dt. And in that case, it splits in two rank 1 matrices, sigma 1 U1 V1 T and sigma 2 U2 VT. And these two matrices are rank 1 matrices, and you can see that the highest singular value, you see root of 45 divided by root of 20, there is a simplification, gives you the, in fact, the best approximation of A at rank 1. Okay, so here I summarize the insights and the main ideas before moving to principal component analysis in general. So the U and V contain orthonormal bases for, in fact, what we call the column space. What is the column space? It's the set of linearly independent columns of A or rows of A. So the real achievement is that those two bases, in fact, they do kind of diagonalize A in a way that you write AD equals U times sigma. And in fact, every matrix, not square, okay, or square, doesn't matter, could be written as a sum of rank 1 matrices with orthogonal U's and V's. Okay. So of course, we are not interested in the particular case where A is a rank 0 matrix, but still it's the level. Now I'll move on to the main dish. I'm talking about principal component analysis in general. So what we have just seen is the singular value decomposition. So what defines principal component analysis is based on singular value decomposition. We say that the principal components of A are, in fact, its singular vectors, left or right, U's and V's. And what we call in abbreviation PCA, for principal component analysis, uses the largest U's connected to the U's and V's in the matrix of that. So remember, we just said that AK is the best rank K approximation tool. So in fact, again, AK solves a kind of matrix optimization problem. I mean, the K-ranked matrix that gets us the closest as possible to A. In statistics, we mainly base our work on studying variance covariance matrices. This is not the case of data science. The SVD is, in fact, at the center of data science. PCA itself is what we call unsupervised learning, because we are mainly using powerful tools of linear algebra to study chunks of the matrix, to decompose the matrix. So when the learning is supervised, in fact, what we call, we have a big set of training data, and we call that deep learning. So supervised learning is deep learning, unsupervised is PCA. Deep learning constructs, in fact, a function that that is trained or obtained from the training set of data. So it constructs a function f that correctly classifies most of that trained data, and then we apply f to the new data. So remember, Eckart-Young said that if B has rank K, then B cannot get you as close than AK to A. But here again, we have to dive into the definition of what we call the norm of a matrix or the magnitude of the matrix. So there are, in fact, three common choices. There are different ways to compute this number, and they may give you different values. So three choices are common. What we call, first of all, the spectral norm, which we call the L2 norm. So the guys on optimization, they know a lot about that, which basically maximize the norm of AX over X. Okay, there is a more common way, which is the Frobenius norm, which basically sets the square roots of the singular value squared, or what we call also the nuclear norm if you remove the square. Okay, ways to do it. Okay, so for example, if you have any matrix A, well, you can just square each one of the items in your matrix, sum them up, and you obtain what we call, you put them under the square root, and you have the Frobenius norm. I forgot the square root. Yes. So the Frobenius norm is just the square root of the differences of the items by one of the matrix, if you wish. Okay, and in fact, from that, you can obtain also beautiful CR factorization, basically. And I forgot how is it used for practice, but I'll move on anyways. So the main part now that is left is to talk about applications. And we have, alhamdulillah, some time left to talk about this methodology. So here we have 2 or 3 applications where we are going to apply these principles. So let me detail the methodology first. So we have n samples, and for each sample we measure n variables. Like, for example, m could be equal to 2 in the case of height and weight problem. So the data matrix A0 has n columns and m rows. For example, you have 1,000 children, and you have m rows. For each one of the kids, you have the height and weight. Okay. Of course, in many applications, these are very, very, very large matrices. One of the first steps is to find the average or the sample mean along each row of the matrix A0, of the data matrix. And on every row, you're going to subtract the mean from all m entries in the row. So we could obtain what we call a centered matrix of data. And on every row, you'd have, of course, now new mean, which is 0, because you just centered it. So, in fact, in statistics, they use the variance covariance matrix, which is simply obtained by multiplying A by AT. So you have the variances on the diagonal and the covariances upper or lower the diagonal. Okay. So let us apply this to our case, in fact. So suppose we have data of 6 children, 6 kids, and we have their height and weight, and we define what we call the variance covariance matrix, which is S equal to AAT divided by n minus 1. N minus 1 is the size of the sample minus 1. Okay. So here in my case, for my application, I obtained this beautiful matrix 20, 25, 25 fold. Of course, it's easy to see that this matrix is symmetric, which means it is basically you have you can obtain beautiful eigenvectors, beautiful eigenvalues. And these eigenvectors and eigenvalues, in fact, because it is squared also, you can use them to get the principal component of single value decomposition of the centered matrix itself. In fact, what the Eckart-Young theorem says is that you can use the U1, which is associated to the largest singular value or the largest eigenvalue of S to obtain the first, let's say, rank 1 approximation of it. So eigenvectors of S, in fact, are singular vectors of A. And the second singular vector U2, of course, is going to be perpendicular. Just because we said that the U matrix in the singular value decomposition contains orthogonal vectors. Okay, so in my case here, for that matrix, I obtained 2 eigenvalues for S, 57 and 3. And you could check that their sum is exactly equal to the trace. And more than this, I obtained the leading eigenvector, which is U1, associated to the largest eigenvalue, 57, which is U given by 0.5608281. And what you could do more is that when you divide the 2 components of this vector, which is almost 8.3 over 5.6, what you can obtain is the directing vector of this beautiful line. And you can see this is the kind of the spread of the data, and you just obtain a good linear approximation to the way the data is spread around the origin. I mean, based on your centered matrix of that. And this first chunk, A1, is the best rank 1 approximation for S. Okay? A critic of this is that, well, computationally speaking, it is a mistake to use PCA or singular value decomposition on the variance covariance matrix. Okay? So in the second example, we'll move beyond this. We're going to apply SVD on the data itself, not on the variance covariance matrix. So we now deal with the data, for example, that summarize the salary grade for I'm missing R here, for a small startup company. So we have basically 2 rows, simple here. The first row indicates the number of years of experience of the employee, and the second row indicates the monthly salary. So here I had an initial data matrix, which has an average row, which is 3 years of experience in average, and 12 as average monthly salary. When we center it, I obtained this matrix, which is basically I have just 3 employees and have 2 rows, just for simplification. But in general, we have 2 large a sample that obtains too many, or let's say a lot of data and a limited number of rows. Okay, so in the following, we will show how to generate the left and right singular vectors of A0. So basically, I computed a first matrix B, which is AAT, which is square, as you see, and more than this, it is positive definite, as you could check out. Similarly for C, which is ATA, and these 2 beautiful matrices B and C, they do share in common 2 eigenvalues, which are sigma 1 square and sigma 2 square, 3 and 1. Does it happen all the time? Yes, it happens all the time. These 2 matrices, they always share common eigenvalues. And these common eigenvalues, they do represent the squares of our singular values. Okay? The eigenvectors of B are going to be acting as our left singular vectors of A. The eigenvectors of C are going to be acting as the right singular vectors of A. Okay? So I'll move on. Now, since we obtained the singular values, I can obtain the eigenvectors of C, first of all, V1, and I kind of normalize, I divide by the norm of V1 and V2. So I have 2 beautiful orthogonal vectors V1 and V2 obtained from C. and I can use them to generate the vectors U corresponding to the left singular vectors. And this is what I did. I have two other beautiful singular vectors, U1 and U2. Their norm is 1, they are orthogonal. So I have the singular vector decomposition for data matrix. Okay. And more than this, I have the biggest chunk, the most important chunk is this A1 approximation, this rank 1 approximation to our matrix A. So A1 here, which is obtained from the largest singular value sigma 1, U1 and V1. This is the closest rank 1 approximation to A0. And of course, since we are in R3, we have to think about what it represents. Okay, so I'll come back to it. So if I sum up A1 and A2, the two matrices obtained, I can verify that I have exactly A0. And the distance from A1, in fact, to our matrix A is given by the lambda 2, or in fact here, the sigma 2, that is the second eigenvector, the second eigenvalue. So the most you could be when you obtain A1 here, the most you could be far from A is just the second or the next singular value you didn't consider. Okay? Here I'm enlarging my data. Okay, it works well for a small sample. Let's deal with a little bit of let's add more things. So this last example extends, in fact, the experience and salary application to include, in fact, age and gender. So let me say that most women, they do complain in their own company that there is a kind of gender discrimination. So basically, we are interested in studying that fact. So I have a small data. I have 10 employees, and well, I have the number of years of experience. I have the which is the first row. I have the monthly salary. I have the age, and I have -1 and 1 for encoding just the fact that it's a male or female, man or woman. So here, in fact, since we have a 10 by 4 or 4 by 10 matrix, we're going to have 4 singular values, okay, which are common. And applying my principle component analysis, I have the first left singular value, which is associated to the largest singular value, 7.57. In my decomposition, what I obtained here is that the 3 remaining values are kind of, well, much lower than the first sigma 1. And more than this, when I computed the variance covariance matrix, I obtained a very low relation between gender and salary, or age, and of course, number of years of experience. So what I observed is that the last, in fact, singular value here obtained is related to the last row, which means gender has almost no importance. So we could observe that gender does not seem to bring much information. Well, it brings some noise, maybe, but there is no, in that small company, there is no kind of gender discrimination about salary. So the fourth component in U1 is relatively, in fact, in U1 here, I'm talking about 0.075, not about before, sorry for not about sigma 4, sorry for if I'm misread these things. So 0.075, you see it's very low compared to the first 3 components, okay? So gender doesn't seem to have any importance. So if I can remove one of the rows, maybe I can have better visualization of what's going on. So basically, this is what I did. So first of all, I'm showing you what I obtained as a best rank 1 approximation on my own matrix of data. This matrix is rank 1, okay? And now, regardless of the gender factor, we may now think of the best way to approximate that. So I'm removing the gender. So after the removal of the gender factor, the data could be said to fit approximately, in fact, in a plane. Why? So I'm moving in 3D now, not in 4D. And I can represent my data in 3 dimensions, okay? In the plane pi 0 here. And how do I obtain pi 0? Remember, in the first representation, when we talked about children, height, and weight, I was able to draw a line in a 2-dimensional space in the plane. So now I'm 3D, maybe I could draw a plane, which slides perfectly between my points. And this is my intention. So from the two left singular vectors I obtained, U1 and U2, well, I obtained the plane. How? Just doing a simple cross product. We see in simple calculus course. Okay, and of course, this plane would pass through the mean point, which is P0 with coordinate 0, 0, because I centered my data matrix before. Okay, so I obtained performing the cross product of U1 and U2, the Cartesian equation, or what we say in general, the equation of this plane, which, as you can see, slides perfectly between my points. Okay, so we can use just the basic tools in Python. There are 3 T's here. I don't know why. So using Python plotting tools, the following figure shows how pi0 slides perfectly between the 3D scatter plot of our data. And the simple SVD function gives you, in Python, gives you your SVD. So I mean your U vectors, your V vector, your singular values, and in 3 dimensions, you can even represent this perfectly. It works well if your data has some kind of linear relation. Okay, so basically, Dr. Mohammed, this is the last slide. So if you have any question, let's go through.
Thank you very much. Thank you, very nice presentation, very useful, and I'm sure everybody, including myself, learned a lot during this very nice presentation. So I open the floor for questions. Please, if you have a question, go ahead. Either raise your hand or you can go ahead and be the bravest, being the first, and ask your question. I think, yes, Dr. Hussein is here, and the admin, I don't know who's the admin, but is he the president or what? The administrator? Who's the admin? I don't know. I'm sure he's not a student. Yes, any question? Oh, this is Abu Saleh. I suspect that.
Hello?
Because your name is admin.
Oh, no, I'm not admin. Yeah, nice presentation, yeah, Dr. Salim. Very excellent presentation. Thank you, very nice. And there are many good ideas and new ideas. Thank you.
Yes, of course, Dr. Sulaiman. What is surprising to me is that we, let's say, let me extend to most of our colleagues, we in optimization, maybe we don't know much or not that much of the stuff that is in fact used in data science. So we can really exploit these ideas to develop the new methods in whether numerical optimization, linear optimization, or stuff like this. The way we look at data before processing algorithms.
Yes, yeah, thank you. Yeah, I think you are right. It's just the same knowledge with different names and just small changes. But it's good to know and to know the application of these methods that we are using. It's good to know all of these things.
Yeah, that's
actually, Dr. Muhammad.
Yeah, go ahead.
It's not only optimization. Also, the numerical linear algebra. It has a lot of numerical linear algebra and these things. So I think it will be a great idea if you do the same. I think presentation in the department. I'm sure different people there'll be more cooperation between different faculty also in the department.
Yes, I agree that numerical linear algebra should be a staple in our course offering, because it's, as you can see, and we have seen and we know, optimization, we need the numerical algebra. But now I think with the buzzwords of deep learning, data science, and so on, it cannot be clearer that we need really a numerical linear algebra to be stable in undergraduate level and the graduate level. Yes, Hajar, go ahead.
Yes,
Hajar,
Doctor, thank you for your nice presentation. And I just have small question that is there any disadvantage for the single factor decomposition?
Well, in fact, this is just the beginning. SVD decomposition is just the beginning. In fact, what we can see, in fact, most of the time, as people in optimization also know, so when we talk about big data, we're not dealing with any kind of matrices. Most of the time, we are dealing with very sparse matrices. So SVD decomposition is just a beginning. And we're dealing with sparse matrices and very large matrices. So we kind of need numerical approaches to this. And this is where, as Dr. Hussein says, numerical linear algebra fits the gap. So we have what we call, for example, Arnoldi iterations to kind of project the matrix into a lower rank or lower dimensional spaces and to work on these spaces, okay, to obtain kind of lower dimensional approximations. So not only we can lower the rank of the matrix with the approximation, but we can lower, work on lower dimensions.
Thank you, Doctor.
Yes, Fatima.
First, I would like to thank Dr. Salim for his useful presentation. Actually, there are many concepts that maybe it is new for me, but I don't know about other students. And I have a question about the energy test. When we want to test the matrix, if it is positive definite. I think it is in slide 8. This test, you mentioned here that we use this to see if this matrix is positive definite. Does it work also for the other cases, if we have negative definite or indefinite matrix?
Well, basically, if talking about negative matrix, the way to test it, you multiply it by -1. As long as I remember, I've done this like about 15 years ago. You multiply it by -1 basically, and if you obtain a matrix that is positive definite there, so you have now the negative of it is negative definite. Correct me if I'm wrong, Dr. Muhammad. I really totally forget about it.
This is I can comment on this. Yes, Doctor, but continue, Dr. Salim. Yes.
So basically, you multiply by -1, you verify that if it's positive definite, then your own original matrix is negative definite. Okay, semi-definite, the condition is a little bit more tricky. So you have these consecutive or leading determinants. They have to be whether always positive or 0, or they have to be in let's say in opposite signs. Correct me if I'm wrong, Dr. Muhammad. I'm honestly missing it.
No, it's no. What you said is correct, but just I want to add that for this test, it is of theoretical importance. It's not practical because you have to check for all x. That is not practical. I mean, but this is, we use it all the time whenever we want to prove positive definiteness, and it is the same for negative definiteness as well. For positive semi-definiteness, as Dr. Salim said, this is relaxed. It's greater than or equal to 0. But this has to be for all x, including 0. But obviously, it is true trivially for 0. It's greater than or equal in the case of 0, but it has to happen for every x. So this is very important in the theoretical aspect of it, which is also very important. But what the other computational parts that tests that Dr. Salim talked about is the one that we usually test. We have to find the decomposition, the numerical linear algebra to test or to see whether a matrix is positive definite or almost positive definite. These are the yes.
So let me
yes.
You have someone else?
Yeah.
Yes, I wanted to say that now that you have some kind of ideas, so knowledge starts when we start asking ourselves, if we understand deeply what we just presented. Now, do you think that honestly you're going to compute all eigenvalues for 1 million bar 10,000 matrices? Of course not.
Of course not.
So that's why numerical linear algebra is going to play a very important role. when we talk about being data.
Yes. Some students, they have a class in 5 minutes. If there is any question, or we can finish now, thanking Dr. Salim for his very, very nice presentation. And hopefully this will be a start for a group, an active group in our department from students and faculty that works in this direction, where optimization, numerical algebra, data science, all of these branches merge together and work together, and hopefully this will be the nucleus, the start of something that will be useful and helpful in the future. Again, I cannot thank you enough, Dr. Salim. I know your time. I know that you dedicated your time, and I thank you very, very, very much. And thank everyone. Thank you for the student. Thank you for the chairman. And I just want to convey the Dr. Abu Saleh. He sent to me that he had to leave because there is something he has to attend to, and he apologized for leaving without saying goodbye. Thank you, everyone, and I hope we will see you next week. And we have a lot of presentations all the way until the end of the semester. Thank you, everyone. Assalamu alaikum.